delta P is equal to 0, that is the momentum is found exactly without any uncertainty, then delta X is equal to h by 4 pi into delta P. So here h by 4 pi into 0, which is equal to infinity. So therefore one is found exactly, then the other one is got maximum uncertainty. So from these two conclusions, what we can say that the simultaneous determination is not possible. Therefore momentum position cannot be measured simultaneously for microscopic particles. In a similar way, this is not only for the position and momentum. There are some properties, they cannot be observed simultaneously. So another example is the energy and time. Therefore, from Heisenberg uncertainty principle, we can write delta E into delta T, which is greater than or equal to h by 4 pi. This is also the uncertainty principle. So here delta E is the uncertainty in energy, delta T is the uncertainty in time, which is also greater than or equal to h by 4 pi, which is similar to the Heisenberg uncertainty principle, which is given by delta X into delta P is greater than or equal to h by 4 pi. Now the question is, why it is impossible to determine simultaneously both position and momentum of a microscopic particle? The answer may be, we do not have sophisticated instruments to measure simultaneously both position and momentum, or it is the inherent property of the microscopic particle. Either one is the answer. How can we explain this problem? Here, this can be explained with understanding visibility. We cannot see any object in dark. In order to view any object in dark, we have to supply light which is fall on the object. The light which is falling on the object, the reflected beam is incident on the observer. Then we can see the image of the particular object, and then we can see the object. So this is the visibility. Now suppose if the object is very small, the necessary condition for this is the smaller the wavelength is required. Suppose if the wavelength is larger, with using this larger wavelength light we are observing a microscopic object, it cannot reflect. So that means the light radiation is directly passing through the object, it cannot reflect, so that we cannot see the object. So the necessary condition to view any small objects is the wavelength should be very small. So keeping it in mind, so let me explain the uncertainty principle. So let us consider this is the nucleus and the electron, and this electron is revolving around the nucleus. So look at this movement. Now my aim is to view this electron. So for viewing this electron, I am incidenting certain radiation on this. Now what is the suitable radiation which can observe the electron? The suitable radiation we can isolate is the wavelength of the electron should be in the dimensions of the electron. So this can be matched with X-rays. We are having so many types of radiations. These are called electromagnetic spectrum. Among these different types of radiations, X-rays are suitable for viewing this electron. So that means the dimensions of the electron will be matched with the wavelength of the X-rays. So therefore, in order to view the electron around the nucleus, we must incident the particular electron by using X-rays. Now, suppose if X-ray is a fall on this electron, what happens? Its wavelength is very small, hence its energy is very large. When this high energetic photon collides with the electron, the path of the electron is changing. So look at this. Before incidenting the X-rays, the path is like this. So if at all this electron was incidented by photon of X-rays, then the path is changing like this. So that means we are trying to look at the electron, but we cannot observe. The expected path is like this, but the electron is deviating from its original path. Hence, we cannot observe. So if at all trying to observe this electron, there is some uncertainty.